Hello friends, in this video we will see about probability and statistics, normal distribution. Like this is a series, this is a fourth video in the series, and normal distribution is the topic. And like a quick recap from the previous sessions, sessions 1 and 3 had the definitions of subjective and objective. Subjective refers to experiences, opinions and judgments that are influenced by personal feelings, perspectives and or interpretations. Objective refers to information, facts or observations that are unbiased, independent of personal opinions and can be verified or measured by multiple observers. So subjective is often associated with individual points of view and can vary from person to person. And objective, it aims to be impartial and based on observable evidence. Statistic is subjective, but subjective opinions come into picture based on the probability. If the probability value is say 75% or thing, expert opinion comes into picture. In that case, the subjective opinions definitely matters. So there are more philosophical discussion and understanding of probability and statistics. Like for that, we can refer to the Plato website, plato.stanford.edu, and search for terms like probability, Bayesian, and more. Like sessions 1 and 3 also had definitions for probability and statistics, and session 3 had the types of charts, and session 2 we saw about types of curves, and session 2, like following slides are going to be belonging to session 2. So in session 2 we saw the terms mount shaped curve and bell shaped curve. Bell shaped curve refers to standard normal distribution, and this means it means inherently symmetric. So bell shaped standard normal distribution, there are various normal distribution. Whenever we refer to the term normal distribution, we always refer to the standard normal distribution, which is bell shaped curve. It has a single peak mode at the center, and the left and the right sides of the distribution are mirror images of each other. And right side, this is a video. So if you see this video, like as the number of discrete events increases, the function begins to resemble a normal distribution. So mount shaped curve. Mount shaped curve typically refers to distribution with a central peak or mode. So and does not necessarily imply symmetry. So here in this case, this is a mount shaped curve, and 1 minute. So this is a mount shaped curve, and here this is not symmetric, so it is skewed to one side. Like right side figure is an asymmetric figure, so this need not necessarily imply symmetry, but a mount shaped curve can also be symmetric. So what is a mount shaped curve means? Indicates that the tail on one side is longer than the other. So here in this case, even though it is asymmetric, for example, I am just telling the tail on the right side of this thing is it looks like a longer tail than the left side part. So there are several distributions apart from normal distribution that could exhibit mount shaped curve. And types of normal distribution, there are various types of normal distribution: standard normal distribution, multivariate normal distribution, non-standard normal distribution. So these are all different truncated normal distribution, log normal, double exponential, and double exponential again got repeated, and skewed, generalized normal distribution, exponential power distribution. So each definition is being mentioned here. So standard normal distribution means mean equal to 0 and the standard deviation is 1. Standard deviation value, it's called a standard normal. Multivariate normal distribution means extension of the normal distribution to multiple dimensions where there are correlated variables. The probability density function involves a mean vector and a covariance matrix. Non-standard normal distribution, any normal distribution that is not standard. It has mean mu and standard deviation sigma other than 0 and 1. Truncated normal distribution, it has been cut off or truncated at one or both ends. Values outside of a specified range are set to 0. Log normal means logarithm of a log normal distribution follows a normal distribution. The log normal distribution is skewed and is often used to model the distribution of stock prices. Double exponential distribution, while not a normal distribution, the Laplace distribution or the double exponential distribution has a similar bell-shaped appearance. It has a peak at the mean and exponential like tails. Double exponential has a definition: skewed, like skewed normal distribution, generalized normal distribution, exponent. Everything has their own definition. Skewed normal distribution means a normal distribution that is skewed, meaning it is not symmetric. And family of distributions, generalized normal distribution means that includes the normal distribution as a special case. Exponential power distribution means a family of distribution that includes normal distribution as a special case. The exponential power distribution introduces a shape parameter that allows for adjusting the tail behavior. In generalized normal distribution, it introduces a shape parameter that allows for varying degrees of tail flatness. So it's important to note that the term normal distribution often refers specifically to the standard normal deviation distribution unless otherwise specified. Other distributions, while related or derived from other normal distribution, may have distinct characteristics or applications. Terms related to normal distribution. So these are the terms which we saw in session 2: head, like tail, and measures of central tendency, measures of dispersion, and symmetry, skewness, kurtosis. Kurtosis is the fatness of the tail of a probability density function or a probability mass function. Skewness is a measure of the extent to which a probability mass function or probability density function leans to one side of its mean. So we see that in the right side figure, there is a right side positive skew means it leans to the right side, and negative skew means the tail leans to the left side. When there is skewness, then in the center there is a mode. The top, the head part is the mode. That is the thing. And in symmetrical distribution, the mean, median, mode, all three values are equal. Measures of dispersion are variance and standard deviation. Like we have seen this definitions for variance and standard deviation. We will see soon. And the head and the tail part is been mentioned here. And dark blue region, in the topmost, the dark blue region is the head part. The uppermost value, that is the marked as head, but it's like a head for like a most, like topmost region I have marked, but it includes this dark portion as well. The tail regions close to the bounds of the random variable, if the probability density function are relatively low therein. So usually it has the form x greater than a or x less than b or a union thereof, and it will have low probabilities. And in probability theory, a probability density function or density of an absolutely continuous variable is function whose value at any given sample or point in the sample space can be interpreted as providing a relative likelihood that the value of the random variable would be equal to that sample. So here there is their interquartile range. IQR means interquartile range Q1, Q3. What is the final value is Q1 into 1.5 minus 1.5 into IQR value, Q1 IQR value, and Q3 is equal to Q3 plus 1.5 times the IQR value. So that is the final value which we define. These things have been discussed previously. Interquartile range, everything. Box plot, that is a box viscous plot, and a probability that a less than or equal to x less than or equal to b is equal to a to b f of x dx. And in probability theory and statistics, the cumulative distributing function of a real valued random variable or just a distribution function is the probability that it will take a value less than or equal to x. So it includes all the values till x. So that is cumulative. Whereas probability density function means that is within a specified value, like for a continuous function. For a discrete variable, the probability mass function is a function that gives the probability that is equal to the exactly some value. So p of x equal to x. Here a to b for continuous variable. Next, like in theory, a discrete random distribution cannot exactly be a normal distribution because the normal distribution is continuous. The probability density function of a normal distribution is a smooth continuous curve. However, in practice, when dealing with discrete data, it is common to approximate a normal distribution for certain situations, especially when the sample size is sufficiently large. In many cases, as per the central limit theorem, the distribution of the sum or average of a large number of independent and identically distributed random variables, even if discrete, tends to approach a normal distribution. This is particularly true as the sample size increases. The larger the sample size, the better the approximation. So while discrete distributions cannot exactly be normal, under certain conditions and with large enough sample sizes, The distribution of the sample mean or sum can closely resemble a normal distribution. This is often used as an approximation in statistical analysis when working with discrete data. We have to keep in mind that the appropriateness of this approximation depends on the characteristics of the original distribution and the specific analysis being conducted. Measures of central tendency, arithmetic mean, and then arithmetic mean is the average of the values, where when there are probabilities, the weighted average of the probabilities is calculated and it is known as the expected value. That is, if P of I is given, probability of I is given, then along with that value, the weighted thing and the value corresponding number has to be multiplied, and then the average value, if it is taken, then it is the expected value. The mean is sensitive to extreme values, outliers, and may not accurately represent the center if the data is skewed. And mu or x naught is the variables that are used to indicate the mean. Mu means population mean and x bar is the statistical mean. And the expected value or the mean of the random variable, the arithmetic mean is the average of the data set. When there are probabilities, the weighted average of the probabilities is calculated and it is known as expected value. It is the mean of the random variable, helps in quantifying long-term behavior of the random variable, which could be recovery from a disease due to drug dosage as in clinical trial. In right side figure, for discrete and continuous, how E of x is calculated is mentioned. E of x is equal to, as mentioned previously, is a summation of xi into P of x is equal to I. Xi represents each possible value of the random variable x. P of x is equal to I. Xi is the probability of the random variable taking on the value xi. The summation is taken over all possible values of x. For continuous random variable, the formula is similar, but instead of a sum, it involves an integral. That is minus infinity to plus infinity x into f of x dx, where f of x is the probability density function of the continuous random variable. The integral is taken over the entire range of possible values of x. Measures of central tendency, median and mode. Mean, like this was mentioned previously, like symmetrical distribution means mean is equal to median is equal to mode. It figure positive skew. Mode is at the top because mode means it is the most often repeated. That's why most often repeated value, the value which is getting repeated again and again. So because of that, the mode is at the top of the curve, and median is at the center. It even though it is not at the top like of the curve, it is at the, it represents the center value, approximate value, the middle value. That's why it's mentioned in the point, like it is a robust measure of central tendency and is often used when dealing with skewed distribution. The positive skewness or negative skewness, the median is the most central most value here in both cases. And like considerations when it should be used, and when what consideration should be taken into account when the median is going to be applied for the normally distributed. So when the data is not normally distributed, at that point of time, median should be taken. Mode means identifies the most frequently occurring value. In probability statistics, mode is useful for describing the central value in categorical or discrete datasets. Some datasets may have multiple modes, multimodal or no mode at all, or measures of central tendencies. And in above figure, this was told and it has been discussed in session 2 as well. And now in this discussion, we are going to see about normal distribution or Gaussian distribution. So normal distribution or Gaussian distribution, it has this value, this function value. F of x is equal to 1 by sigma root 2 pi e power minus half into x minus mu by sigma the whole square. Mu is mean or expectation, and sigma is standard deviation, and pi has the value 3.14. And the random variable with the Gaussian distribution is said to be normally distributed and is called a normal deviate. Population versus sample variance. For a normally distributed curve, the population variance and sample variance are as follows: sigma square and a square. Sigma square is equal to 1 by n into summation of I is equal to 1 to n xi minus mu the whole square. So that is E of expected, it could be said like E of xi minus mu the whole square. And where sigma square is population variance and n is the number of data points in the population, and each data point in the population is xi and mu is population mean. Sample variance is s square. Sample variance is calculated similarly but with a correlation factor divided by n minus 1 instead of n. So why n minus 1? Because in order to account for the fact that we are estimating the population variance from a sample. So s square is equal to 1 by n minus 1 in summation of I is equal to 1 to n xi minus x bar the whole square. So s square is equal to s square is sample variance, n is number of data points in the sample, xi is each individual data point in the sample, x bar is a sample mean. In both formulas, xi minus mu or xi minus x bar represents the difference between each data point and the mean, and the squared differences are averaged. The division by n for population variance or n minus 1 for sample variance is part of the calculation to obtain the average. We have to keep in mind that the square root of the variance is the standard deviation sigma, which provides a measure of the average deviation from the mean in the original units of the data. So this is simple. Both both variants are going to have a similar formula, except for sample variance is going to have n minus 1. So we will see in the next few slides when till what value we can use n minus 1, after which can we use the n value. And central limit theorem. In probability theory, central limit theorem states that under appropriate conditions, the distribution of a normalized version of the sample mean converges to standard normal distribution. So central limit theorem states that regardless of the shape of the population distribution, the distribution of the sum or average of a large enough number of independent identically distributed random variables will be approximately normally distributed. So whatever the form of population distribution, the sampling distribution tends to be Gaussian, and its dispersion is given by the central limit theorem. So central limit theorem it's plain and simple. So the distribution of a normalized version of the sample mean converges to sample mean. From the sample we are going to we are estimating how what will happen to the sample mean, how the distribution of the normalized version of the sample mean will be. So it converges to a standard normal distribution, and central limit theorem states that regardless of the shape of the population distribution, so population distribution in this case below figure, if you see, it is by it is not a bell-shaped curve. So what are this shape is not bell-shaped. So whatever the shape of regardless of the shape of the population distribution, the distribution of the sum or average of a large enough number of independent identically distributed random variables, that's why it's been mentioned like x bar everywhere. So identically distributed random variables will be approximately normally distributed. So sampling distribution of the mean, and then when till what point we will be using that n minus 1, when it is not like a like 2 slides back we saw when till what point we will be using n minus 1, the sample. So n minus 1 will be like in some cases, if the number of samples which we draw from the population is going to be around 30, we will say we will use the formula n instead of n minus 1. So this number is not a standard definition, it's just a thumb rule. So number 30 is often associated with the rule of thumb in statistics, specifically in the context of central limit theorem and the use of normal distributions. The rule of thumb suggests that if you have a sample size of 30 or more, you can often assume the sample distribution of the mean is approximately normally distributed, even if the underlying population distribution is not normal. This rule becomes relevant in scenarios when we are making inferences about population parameters, particularly in the population mean. The standard deviation of the sample mean is given by sigma by root n. So sigma by the standard deviation of the sample mean is given by sigma by root n, where n is the sample size. When the sample size is large enough, typically n greater than or equal to 10, central limit theorem states that distribution approaches normal distribution regardless of the shape of the population distribution. The formula for the standard error of the mean, which represents the standard deviation of the sample mean, is given by sigma by root n. Here sigma standard error is standard error of the mean, sigma is population standard deviation, n is the sample size. It is important to note that the choice of 30 as a threshold is somewhat arbitrary, and the applicability of the rule of thumb depends on factors such as the shape of the population distribution and the specific goals of the analysis. In practice, if the population distribution is known to be approximately normal, even smaller sample sizes can often be sufficient for normality assumptions. Additionally, larger sample sizes provide more robust results. Moments and moment generating functions. This is the final slide. So in mathematics, the moments of a function are certain quantitative measures that characterizes the shape of the function's graph. In probability theory and statistics, a central moment is a moment of a probability distribution of a random variable about the random variable's mean. That is, it is the expected value of a specified integer power of the deviation from the random variable from the mean. So univariate moments, the nth moment right side, the nth moment about the mean of a real valued random variable x is the quantity qn, that is equal to e of x minus e of x the whole power n, where e is the expectation operator. For a continuous univariate probability distribution with probability density function f of x, the nth moment about the mean mu is mu n is equal to e of x minus e of x power n, equal to minus infinity to plus infinity x minus mu the whole power n by x minus mu the whole power n into f of x dx. For random variables that have no mean, such as the Cauchy distribution, the central moments are not defined. The final few central moments have intuitive interpretations. Zeroth central moment mu naught is 1. First central moment mu 1 is 0. It should not be confused with the first raw moment or the expected value. The second central moment mu 2 is the variance and is often denoted by sigma square. Sigma represents standard deviation. Third and fourth central moments are used to define the standardized moments, which are used to define skewness and kurtosis. So this is for our general understanding, and the moments and moment generating functions can be discussed in a separate topic. The various moments from one set of values by which the properties of probability distribution can be usefully characterized are given on the right side. So non-central moment what value and central moment is what value, and significance of moments. So this was mentioned in the first picture in the top right side. And finally, the moment generating function of a random variable x is a mathematical function that provides a systematic way to derive the moments of x. It simplifies the process and provides a unified framework for calculation. So, and finally, if you see for other distributions other than standard normal distribution, for other distribution, Bernoulli distribution, geometric distribution, binomial, negative binomial, what are the moment generating functions and the characteristic functions. And I mentioned, like I have added 2 more points. So previously this was the last slide which was there. So Chebyshev's inequality or theorem. So Chebyshev's inequality, it's also known as Chebyshev's theorem, is a fundamental result in probability statistics. It provides an upper bound on the probability that a random variable deviates from its mean by more than a certain amount, regardless of the shape of the distribution. So what is the probability that a random variable deviates from its mean by more than a certain amount, regardless of the shape of the distribution? Chebyshev's inequality is particularly useful when the distribution's properties are not well known, or when dealing with any distribution, including those that are not normal. The statement of Chebyshev's inequality is as follows: for any random variable with a finite mean mu and a finite non-zero variance sigma square, the probability that the random variable deviates from its mean by more than k standard deviations is at most 1 by k square for k greater than 1. So we will take a finite mean mu, and we will assume like finite non-zero variance sigma square. Let us take the variance as 9. So the standard deviation is 3. The probability that the random variable deviates from its mean by 3 standard deviations is at most 1 by 9. So the 1 by 9 means that is equal to 0.111. 0.11, and this k value should be greater than 1. So 0.11 is the outlier for deviates from the mean by more than k standard deviation. So for 3 standard, for normal distribution, for 3 standard deviations, we see that 0.9199, that is 1 minus 0.11 means you will get 0.99. So 0.99 is 0.9988 something. So that is 99.88% values will be within the normal distribution, and only the remaining value is going to be there as outliers. In mathematical terms, the same thing has been what the topic which has been explained, it has been mentioned in a mathematical format. And then empirical rule. So the empirical rule is a statistical guideline that describes the approximate percentage of values within a certain number of standard deviations from the mean in a normal distribution. The rule is based on the properties of a normal distribution and is particularly useful when dealing with data that is approximately normally distributed. So it is known as 68, 95, 99.7 rule. So 68% of data falls within one standard deviation, approximately 95% falls within two standard deviations, and approximately 99.74% falls within three standard deviations. Symmetry of the normal distribution. Empirical rule is based on the symmetry of the normal distribution. It is perfect in a perfectly normal distribution. Data is symmetrically distributed around the mean. Use with Z scores. So Z scores are used in hypothesis testing, which will be covered later. Z scores, standard scores, are often used in conjunction with empirical rule. A Z score indicates how many standard deviations a data point is from the mean. For example, it is a test statistics, sample statistic. For example, Z score of 1 corresponds to 1 standard deviation above the mean. Applicability. The empirical rule is most accurate for data that is close to a perfect normal distribution. It provides a quick and easy way to estimate the proportion of data within the different ranges without performing detailed calculations. So how Chebyshev's inequality is going to be like against empirical rule. Scope and applicability, specificity, comparative precision, use of Z scores. Chebyshev's inequality is a more general rule, applies to any distribution. Empirical applies to only normal distributions. Specificity, Chebyshev's inequality gives a universal bound for that, but tends to be more conservative, providing a wider range of possible values for proportion of data within a certain number of standard deviations. Whereas empirical rule is more specific to normal and provides more precise estimates for the proportion of data within 1, 2, and 3 standard deviations. Comparative precision, Chebyshev's is less precise in the terms of estimating the percentage of data within specific ranges, but it is more robust when distributional information is limited. It is very robust, means it is very useful. So empirical rule, it provides more precise estimates for normally distributed data, but relies on the assumption that the data follows a normal distribution. Use of Z scores. Both rules make use of standard deviations and Z scores, number of standard deviations from the mean, to express the spread of the data. So Z scores, like as I mentioned previously, is useful mainly in hypothesis testing for comparing and interpreting data. And thanks lot for watching. And images and content are mostly based on Creative Commons and open source license from the internet from various resources. The content has been gathered, and I thank all the contributors for the content. Thank you.